Okay, so today we're going to use solving systems of equations using elimination. It's we talked about in our last lesson how to solve systems of equations using substitution, and so we're going to try using the second method. When we do want to use this method, we want to make sure that we have our equations in standard form, which remember from the last unit is ax plus by, which is equal to c. So you want to make sure you have your like terms all put together for our x's and our y's, and then everything else that doesn't have variable put on the right side of our equation. So looking at our steps for solving systems using elimination, we want to make sure that we line up vertically the like terms and equal sign for the two equations. And this step is really key to keep our problem organized and make sure that we don't miss a step. Then we also want to choose a variable to eliminate. Sometimes, not always, but sometimes we're going to have to use multiplication to make sure that this variable has the same coefficient on both sides of the equation. And that will make more sense later as we try a few problems. Then we want to add or subtract the like terms vertically to eliminate the chosen variable. Okay, adding is always going to be easier than subtracting, and we'll see when adding is a better one to choose, or subtraction may be easier. Then we want to solve the equation that is left. In this equation, you're only going to have one variable because you eliminated either x or y. And then once you have that, you want to substitute or put your answer back into the original equation and solve for your remaining variable. And then once again, just like in substitution method, we're left with an ordered pair. Okay, so you can write your x value and then your y, and that's the point where our lines intersect. So let's take a look here at our first example. So we want to use the elimination method to solve this system of equations, which is 3x plus y is equal to -9, and negative 3x minus 2y is equal to 12. So you see here in this first step, we lined up our like terms and our equal signs vertically. Okay, so we have our x's, then our y's, and our equal signs, and that's equal to our numbers here. And this step is very key in making sure you complete this problem correctly. Now we want to look at our terms, and we see that our x's here have coefficients that are very similar. They both have a coefficient of 3. This first one has a positive coefficient of 3. This one has a negative 3 for its coefficient. And we know, which we've talked about before, that these are additive inverses, meaning that they add up to 0. So we want to add these two so that we can eliminate our x's. So we're going to add the two equations together. So we have 3x plus a negative 3x, which is going to give us a 0x, so we're not even going to write that here. And then we have y plus a negative 2y. We want to make sure to include that negative sign out front. So we have y plus a negative 2y, which is going to give us a negative y. And then we have our equal sign, that remains the same. And then a negative 9 plus 12y, which gives us 3. So then we have, using division, we're going to divide by a negative 1 or multiply by a negative 1. We have y is equal to negative 3. Now that you have that solution for one of your variables, very similar to our method of substitution, we're going to plug in that value for y into one of the equations and get our value for x. So here we chose one of the original equations. We decided here to choose the one that just had the y by itself without a coefficient, or with a coefficient of 1, I should say. So 3x plus y is equal to negative 9. Plug in that y equals negative 3, and you have 3x plus a negative 3 is equal to negative 9. And we want to solve for x now. So we add 3 to both sides, which would give us 3x is equal to negative 6, and then that leaves us with dividing by 3, so x is equal to negative 2. Okay, so we substituted for y and solved for x. That gives us our solution, which we always want to write as an ordered pair. We have our x value, which is negative 2, and our y value, which is negative 3. That, once again, as a reminder, is our point of intersection for our two equations that we were given. Moving on to the next example, we notice here, if we're looking at our example, that it's not as easy as in our first example to know which variable we want to eliminate. So what we're going to have to do in this case is to multiply one of our equations in order to multiply one or both of our equations in order to get the same coefficient. So looking here at this first example, to eliminate the n term, that's the one we're deciding to eliminate, is our n variable, we want to make them additive inverses by multiplying. So they take this first example, or this first equation, 2m plus 4n is equal to negative 4, and they multiply it by 5. So 2m times 5 is 10m, 4n times 5 is 20n, negative 4 times 5 is negative 20, which gives us this resulting equation. Then they want to multiply this second equation by negative 4 in order to get a negative 20n. So negative 4 times 3m, negative 12, 5n times negative 4 is negative 20, and negative 3 times negative 4 gives you 12. So now you see that by doing this multiplication we have a positive 20n and negative 20n. That makes those additive inverses, which means that they're going to be eliminated once we add them. So we have negative 2m is equal to negative 8 when we add the two equations. Then we want to divide by negative 2m, or negative 2, I'm sorry, to get m by itself. So m is equal to 4, because negative 8 divided by negative 2 will give us a positive 4. Now that you have that value for m, you want to substitute back into one of your original equations. So here we choose 2m plus 4n is equal to negative 4. That's the equation we're going to plug this value of m in for. M is equal to 4, so 2 times 4 plus 4n is equal to negative 4. Solve down for n. We find that n is equal to negative 3. So now that we have that value for n and m, we can write it as an ordered pair, where m is similar to our x, so it's going to come first. So we have 4, comma, negative 3, because n is like our y value. So this is the solution for where these two equations would intersect on a graph. Okay, so now it's your turn to try an example. I want you to solve the system of equations using elimination. I'll give you a hint that it's going to be the easiest to get these y's to eliminate. So you got to think of, how can I get a common coefficient with the ones that you have now? So go ahead and take a minute, pause the video, try solving that system of equations. If you need to, feel free to go back and look at our previous examples for any help. Okay, let's take a look at our solution. So we had our original equations, negative 3x plus 5y equals 6, and 5x minus 10y equals 0. And we want to eliminate our y value. So, our variable, I should say. So in order to do that, I'm just going to multiply this first equation by 2 in order to get a positive 10y. And actually, this here should be a negative. So multiplying it by 2 gives a 3x, negative 3x times 2 is going to give me a negative 6x. 5y times 2 is a positive 10y, and a 6 times 2 is 12. So adding these two together, I'm going to have negative 6x plus 5x is going to give me a plus, once again here, a negative 1x. And then my positive 10y and negative 10y are additive inverses, which is what we wanted. So that will eliminate my y, giving me 0y, or just 0. And then 12 plus 0 gives me 12. So I have negative x is equal to 12. Divide or multiply by a negative 1 gives me x is equal to negative 12. From there, I'm going to choose one of my original equations, which I chose negative 3x plus 5y is equal to 6. I'm plugging in this negative 12 that I got for my x value to figure out what my y value will be. So negative 3 times negative 12 gives me 36 plus 5y equals 6. And then from here, solve for y. So I have 5y is equal to 42. Divide by 5, y is equal to 8.4. So my solution is the point negative 12, comma 8.4. So now that we have completed that example, we're going to look at some different cases that we may run into when we use the system, or using the method of elimination. So if I start with the equations negative 3x plus 5y equals 6 and 6x minus 10y equals 0, and I want to multiply this first equation by 2, which will give me negative 3x times 2 is negative 6x, 5y times 2 is 10y, and 6 times 2 is 12. So now that I have these two equations and I see that my coefficients actually for both x and y are additive inverses, then we'll be able to eliminate. So if I add these two together, I get negative 6x plus 6x, which will give me 0x, 10y plus negative 10y, which will give me 0y. So then all I have on my left side of the equation is 0, and 12 plus 0 is 12. Now looking at this statement, 0 equals 12, we know that is a false statement. 0 can never equal 12. And since our two variables eliminated, we see that this is a false statement. And this means that the two equations in the system represent parallel lines because there is no solution. We can't find a value for x and y that will work for both of our equations. So that must mean that they don't intersect, which means that our two equations here are parallel. So in that case, we would just say no solution, parallel lines. Okay, looking at our second example here, we have similar equations, except for now instead of a 0 here we have a negative 12. So once again we want to multiply this first equation by 2, so that gives us negative 6x plus 10y equals 12, 6x minus 10y equals negative 12. And once again we see our coefficients for our x and our y are additive inverses. So when we add them, both the x and y variables will be eliminated, leaving us with 0. And we also see that here 12 plus a negative 12 gives me 0. So 0 equals 0. We see that this equation is always true, right? 0 will always equal 0. So that must mean that our two original equations we are given are the same line. And we know that when we have the same line, that means that there is infinite number of solutions. Okay, so when you get to examples in class that are similar to this, we just want to write infinite number of solutions and we're good to go there.